Thanks for coming to this Steam event tonight. I apologize that we're about 15 minutes late. As most of y'all know, the World Series is going on right now, and this room was packed until about 7:45. We didn't even get to do anything, so sorry for being late. We've got a great evening ahead, so thanks for coming out. My name is Michael Lang, I'll be your MC. The way this is going to work is we'll have a speaker for about 20 minutes, and then it becomes a free-for-all. He'll have a presentation for a little while, and then it's, pummel him with questions. The more questions, the better. The more stumpers, the more, the tougher it gets, the better it's going to be, the more entertaining it's going to be for y'all. This is not designed as a lecture. It's designed as a conversation, so we really want you to get involved. We run 2 Steam events a month right now. There's this one here at TSVQs, and then we have another one out at His Cafe in Bellevue. The one that we have next week on Thursday is Future Cities. It's an engaging learning experience where middle school students mentored by STEM professionals create cities of the future. It incorporates of course, science, technology, engineering, arts, and math, and it's going to be a terrific program. So if y'all are interested about what the future of cities looks like, and specifically if you know any folks that have middle-aged schools, and school children, it's going to be especially useful. We have sign-in and registration in the back. It's $10 if you haven't done that. We appreciate that on the way out. That goes partly to our speaker, to the raffle prizes that we have. So we really encourage you to do that. And then there are raffle tickets at the back. I'll pass them out just before the raffle. Okay, great.
As well as the survey.
Stephen has homework for us, so everybody should have a graph paper.
Not homework.
He'll explain what that's for in a bit. Graph paper
and computer paper. Yep.
Okay.
Yep.
So let's get started. Stephen is CTO of Stabilitas
Ventures.
Pronounce that correctly? It's artificial intelligence company looking at kind of security. That's how I'm describing it.
Fair enough. That's close enough.
Looking at security and people, human assets on the ground. But he's also been a geek and a nerd since a very, very, very young age. I'll describe that in a bit. And he's also a captain in the Army Reserve. So he's got a very interesting background. I hope he'll share some of that with you. Without anything else, welcome, Steve.
Alrighty, yeah, thanks, Michael. Appreciate it. Oh, you don't need to applaud for me yet. Wait until after this epic event. So the homework, as Michael said, it's a little bit of interactivity. If you don't have a piece of graph paper and a piece of computer paper and something to write with in front of you, please raise your hand and somebody will get some to you. Everybody good? Everybody good? Oh, we need one. Okay. And Michael, if you could get one for the gentleman in the awesome sweater. Alrighty. Okay, yeah, so let's get going here. Tonight, I want to talk about the art and science of math. Figured that would fit into the STEAM kind of idea a little bit. I am the CTO of Stabilitas Ventures. That's not as exciting as it sounds. There's really only 3 of us, so we all have really cool titles. But we are looking to grow soon and do interesting things. Hopefully you'll hear about us in the future. Before we get going, I wanted to establish my nerd cred here. This was me not too many years ago at another internet startup. I was working probably 22-hour days and drinking too much Mountain Dew. I like this picture because actually I was a lot cooler back then. I have been coding since I was 6 years old. We'll tell a little bit more about that at the end, but the stuff I'm going to talk about today is, oh, something interesting is happening. Oh, is he going to score? Oh boy, this is going to be a nail biter. All right, the stuff I'm going to talk about tonight is all stuff that I played with as a middle schooler and high schooler with computers. This is stuff that I found incredibly interesting for all sorts of nerdly reasons. But one of the things that I think is really cool about it is all the stuff I'm going to talk about creates really pretty pictures, just good-looking stuff, good-looking art, and it's all mathematically based. So we're going to talk about these 4 things specifically. And I've got some more in the appendix slides if we get to it, but I'm going to tell you that that dragon right there, this pretty whatever this is, this mountain, and these eggs are all virtually identical when it comes to the math. It'll make sense by the end. All right. I do have to do a quick math review. I apologize for this. This, I promise, will be the only mathy stuff that we end up talking about tonight, okay? We need to talk about some algebra. Everybody remember their algebra classes, the variables like x, and you want to say something like x equals 10. Awesome. What happens when you want to add 1 to x? You do something like this. X equals x plus 1. So we take the old value of x, add 1, and that's the new value of x. Now let's do this 100 times. We use a mathematical notation like this. We say the previous version of x, n minus 1, plus 1 is equal to the current value of x. Okay, so a little bit of animation there. Does this make sense to everybody? Because this is the crux of the rest of the evening. Okay, if we did this 100 times, we would say that 100th version of x is equivalent to the 99th version of x plus 1. When we do this over and over, we call this iteration. Okay? Everything that I show you tonight is based on iteration. Iteration can be equations, like we just showed, but it can also be actions, like walking. What is walking? But putting one foot in front of the other, and then you put one foot in front of the other, one foot in front of the other. You just iterate, taking a single step. Make sense? Good. Enough of this math stuff. Let's get to the fun part. We're going to talk about something here. The first fractal that we talked about tonight is something that I used to do when I was young and we still had dot matrix printers. Remember dot matrix printers? Sounded like a war going off under your desk when they were printing out, and they had that fan fold paper. Yeah. So first, fractals. Everybody heard the term before? Okay. So in this case, specifically, we're going to talk about a fractal curve. What a fractal curve is something that is made up of simple lines that put together exhibit recursive self-similarity, which means the big version looks like the small version, looks like the smaller version. But with those simple lines, we get emergent complexity. Blah. What does that all mean? What it means is something like this. We take this V shape, and you notice in generation 2, the blue line there is the previous shape, but we make each line a V itself. See the pattern in there? So each line is replaced by a V. And then the next time around, we replace each one of those lines with a V. So what was a vertical line here becomes a V here. What was a vertical line here becomes a V here. And you keep doing that. If you did that enough, you'd end up with this shape, which is called the dragon curve. So hence the dragon. How do you get from this V to this snowflake-looking beautiful piece of modern art? Well, it works like this. Here's kind of an animated version. You can see how it keeps taking shape. So now that's that green thing you saw before. And as it rolls back out, you can see how it's made up of the simpler pieces until we get back to the V. Do what, sorry? Do what? Show the video again? Yeah. Now, the next step, we're actually going to make this ourselves. Yeah. We'll let it go through one more time here. Good? Okay. Let's make one. So this is what I used to do as a kid. I didn't even know I was making fractals. How cool was I? I want you to take your computer paper there and tear off one of the dotted perforated things on the sides. I don't know if anybody else dealt a lot with computer paper back in the day, but you know, before you handed in your report to school or you handed in the spreadsheet printed out to your boss, you'd always have to tear off these little track things that the spokes use to advance the paper through, right? What did you all do with them? Throw them away? Yeah, what I used to do is fold them. So when you have one of these things, I forgot to get one myself. Oh, thanks, darling. Okay. You have one of these things. What I want you to do, hold it up in front of you. Say, hi, piece of paper. I want you to take the top and fold it down to the bottom, towards you. Fold it in half. Once you've done that, I want you to do exactly the same thing again. Take the top and towards you, fold it down again. And then do it again. And then do it one more time. Or if you're like my wife, she tries to go one more because she just likes to best me at these sorts of things. Yeah, see, she's doing it. All right, so now you should have what you see at the very end there. You should have a little almost square of piece of paper, right? Okay, now we're actually going to make the dragon. What I want you to do is unfold that last half you made by 90 degrees. So you end up with this kind of gamma shape here, this L, upside down L. Then I want you to unfold that whole L 90 degrees. So now you've got something like the Big Dipper, right? And then unfold that 90 degrees. And now you've got a shape that's kind of weird. Boy, I can't even do my own experiment here. There we go. All right, so now you've got something that looks like this. Do it again. Now we'll show this, what this looks like unfolding in video. This might make it a little bit easier. So this is the unfolding that you were doing with each step. So if you see in this video, what's actually happening is you're taking the entire shape that you made and you're duplicating it 90 degrees out. With the paper in real life, it just means you're unfolding your folds 90 degrees, okay? And if you keep doing this, you start seeing that original green shape take shape, okay? While this is going, I'll talk a little bit more about these. These fractal curves are made up of one-dimensional lines that you start folding into 2 dimensions in a self-repeating pattern. The dragon is not the only one you can make. If you took your piece of paper and the first fold you went towards you, and the second fold you went backwards, then forwards, then backwards, and then you started unfolding, you'd get a totally different kind of pattern. One of the more famous ones is something called Cook's snowflake. If you unfold it, it ends up looking like a snowflake, but it's fractal because any piece of the thing is made up of pieces just like it, only smaller. Okay? So that's the dragon curve, and that's a fractal we can't really make anymore because we don't have awesome computer paper like we had in the 80s. But if we did, we could make fractals just sitting at your desk wasting time while things are printing out, which was, I am a nerd, how I spent an awful lot of my childhood making these things going. So yeah, there's your introduction to practical fractals. Let's talk about a little more interesting fractal, though. Let's make it a little more colorful, a little more interesting than just a piece of computer paper. We're going to talk about something called the Mandelbrot set. You've probably seen a picture like this before, especially if you were a college student in the early 90s when color posters of this thing were incredibly popular, almost as popular as Kathy Ireland posters, at least if you went to the Milwaukee School of Engineering in 1992. The Mandelbrot set is named after a guy named Benoit Mandelbrot, but of course in America we mispronounce it and we say Mandelbrot. Fair enough. He didn't actually invent it. He just talked about it a lot in a book that I'll show at the end of the presentation. But in this one, instead of doing an action, folding and unfolding paper, we're back to math. In this case, we iterate this equation z squared plus c on the complex plane. I'm not going to explain that unless you really want me to at the end of the presentation, because that starts getting into nasty math. But if you do this, if you run this equation bunches of thousands or millions of times, you get a picture. Oh, that doesn't look much like our poster, does it? This is actually the first rendering of the Mandelbrot set. Happened in 1978, done on a teletype machine that had a lot of that kind of computer paper in it. That's what they got. As computers got better and we started being able to do color graphics more easily, it ended up looking like that. Here's the cool part about this fractal. This little dot right here, see that black dot? That's actually another version of the entire Mandelbrot set. We're about to dive in here. We're going to zoom deep in, and I want you to keep an eye out for this shape, this kind of weird heart and circle shape, okay? Because you're going to see it a bunch of times in this zoom that we do. Here we go. There's some. There's one. Going deeper, going deeper. There's probably some in there. Oh, let's see. Keep going in this spiral. Oh, there's one. Here's the punchline of this. Every time you saw that Mandelbrot set shape, that weird heart and circle shape, if you zoomed into that one, you would find all these same patterns all the way down to infinity. You ever heard it's turtles all the way down? Yeah, it's actually Mandelbrot sets all the way down. It's not turtles, just so you know. Okay, the Mandelbrot set is a virtual world. It doesn't exist. This math doesn't exist in the real world at all. This is a fictional imaginary place that is completely built out of z equals z squared plus c, executed millions upon millions of times. When I first rendered a Mandelbrot set way back in the mid-'80s somewhere, that initial picture up here took my poor little computer 13 hours to draw. If I had used that same computer to do that zoom that we just saw, we'd probably still be waiting for it today, 30 years later. I'm not exaggerating. I'm not exaggerating at all. The math behind that is incredible, but it's just z equals z squared plus c. You could actually draw this thing on some graph paper. We're not using the graph paper for that. But you could do that just by hand calculating this stuff. Just take a while. And yet there is infinite, oops, let's go back. There is infinite complexity in here to the point where mathematical explorers have actually named the different parts. We have the scepter valley here, named for the little scepter kinds of structures that come out. We have the double spiral valley. You saw the kind of double spiral patterns that we saw in there. Up here, over here, we have the elephant valley, which is a much more polite name than what it actually looks like. But there's all sorts of structures in here that look just like the Mandelbrot set in other places. Here are just some examples of a zoomed-in view. I want to pay special attention to this line shooting out the front of the thing where you have another Mandelbrot set. Turns out that one and that one are also the same thing. The black part of the Mandelbrot set is actually the Mandelbrot set. The color just represents the number of times that you iterated on the equation elsewhere. Getting too mathy, I know, but oh, crap. I went ahead. There we go. This line going out here goes forever. There is no end to the black line. It just gets thinner and thinner and thinner and thinner as it goes. As it gets thinner and thinner and thinner, we get smaller and smaller and smaller Mandelbrot sets. And yet, each one of those contains the whole thing again. It's just amazing. How does this happen from z equals z squared plus c? Chris, you have a question?
I'm curious if I should know this, but what is the c? How does changing the constant affect?
Okay, so the question is the c part in the equation. How does that change things? I am going to not answer that right now, but remind me at the end, and we'll talk about that. Okay. That has to do with the imaginary mathematics and behind it. Why I called this imaginary art, because imaginary numbers are involved and blah blah blah. But yeah, we'll talk about it at the end. after we get through the rest of it. What is Z0? Good question. Z0 is 0. And C is the coordinate on the complex plane. I guess I'm talking about it anyway. Okay, so plotting this thing. Let me go back. Here we go. So plotting the Mandelbrot set, you know, X and Y is how we usually think of things. But in imaginary numbers, X is the real component of the imaginary number. Y is the imaginary component. So C, the constant that you start with, is the coordinate in the complex plane, we call that. Instead of the Cartesian plane, we call it the complex plane.
If Z0 was 0 and C is 0, you don't go anywhere.
You don't go anywhere, yeah. And that is right, I believe that's right here at that cusp there. That's why this line goes to infinity, just shooting out, because the math just says, yep, it just keeps collapsing to 0. As you run the thing, the color outside here is a measurement of how fast that equation escaped to infinity. At some places on this map, you start running that equation and the answer just gets freaking huge, super fast. In other places, the equation stays at a small finite number. If it stays at a small finite number, we paint it black. If it escapes to infinity, we paint it a color, and the brightness of the color indicates how quickly it escapes to infinity. Okay? Obviously, you can't measure infinity, so we have some approximations. And what it turns out is if you iterate on the equation 20 times and the number that you get has exceeded 4, like the magnitude of the line on the complex plane has exceeded 4, it's going to escape to infinity. And then you color it based on how big the number is at that point. If it stays under 4, after 20 iterations, you just go ahead and paint it black. You get more precise resolution on the colors and everything if you run the equation more times than just 20 though. Okay. What's fascinating is the computer hardware we have today, your graphics card or your graphics chip in your laptop is capable of running Mandelbrot set calculations so fast that you can actually be doing a live zoom into the Mandelbrot set and put that on the sides of a cube, rotating and bouncing around on your screen, and it keeps up with that. Even though my computer would have taken over 30 years to generate the same thing before. It's incredible. Let's go. All right, so that's the Mandelbrot set. Goes on forever. You ever want to do some real world exploring? This is a great place to do it. A lot of people have taken this representation, the colors, and changed it to height. And they've shown what a Mandelbrot terrain would look like. Imagine the mountains, like the height of the mountain is how bright the thing is, so darker areas are lower. Okay? You could actually create a virtual world that was really oddly shaped. Or you could create a virtual world that looks a little more realistic. And that's the next fractal I want to talk about. Something called fractal terrains. You don't even have to have William Shatner around. Why is he saying William Shatner? Well, who's seen Star Trek II, The Wrath of Khan? That's the one with the Genesis device. Remember that whole thing? Khan! Okay. In the movie, this was back, what, 1982, 1983, somewhere in there. Industrial Light and Magic, famous for doing the Star Trek effects, started by George Lucas for Star Wars effects. Wow, shoot me. They generated a whole virtual planet using fractals to put in the movie. This is a chunk of the movie where the scientists in charge of the Genesis device are giving a little talk about their thing. That moon there that looks really chintzy and kind of crappy by today's standards was just the height of technology in 1982. And this was a virtual world completely created inside of a computer. All the craters and everything created by the computer using fractals. As we pan over here, eventually those rocky mountains are going to turn a little bit smoother as the Genesis device turns the dead world into a living world. This is all part of the plot of the Star Trek movie, don't mind it. Yeah, we've got water there. You couldn't really see it really easily, but this is all water and nice kind of rolling hills. Yeah. Now we're going to talk about how to make your own virtual world. We use an algorithm called midpoint displacement. It's just iterative. What you do is you take a grid. Again, we're not doing this with the graph paper, that's for something later. But you could do this. You take the grid, you find the corners of the grid, and then find the center point of those corners. That would be this guy. And you raise or lower that point by a random amount. Just throw a die. Say if it's less than 3, it goes down. If it's greater than 4, it goes up. Okay? Less than, you know what I mean. Once you do that, you find the midpoint, or you find the ends of the lines around that, and you do the same thing. Randomly raise or lower. Once you've done that, you've done the middle point and you've done the diamond coordinates around it, what I want you to do is take that grid and divide it up into 4 grids. And for each of those 4 grids, I want you to do exactly the same thing. Okay? So notice where it says divide by 2 here, see that center point that's darkened? That's just like this, except instead of finding the midpoint of this whole big square, you found it on this littler square. Okay? And then you find the endpoints of the lines around it. Same thing. When you've done that, I want you to take the resulting grid and divide each of these squares into 4 squares itself. So you keep quartering the grid, and you're making more and more little grids out of it. You're making more and more grids. It expands by the powers of 2. So you start out with 1 grid, and after the first iteration, you find 4 grids. That's 2 squared. And then with the next one, when you subdivide all that, you're going to find that you have 16. 2 to the 4th. Okay, you just keep going down like that. When you've done this, oh, sorry, we call this, by the way, we call this style of iteration, we call it recursion. That's where you take the problem and then you apply, or you take an operation on a problem and you apply the operation successively on smaller pieces as you go down. Okay? If you do this a whole bunch of times and you divide that grid, that piece of grid paper, to the point where you're dealing with squares that are the size of a single pixel, you'll end up with something like this, which looks an awful lot like the beginning of that stupid video from Star Trek II, doesn't it? Now this is kind of rocky. That doesn't really make for pretty pictures. Maybe this is not the place that Michael's going to plant his lunar space elevator, because that'd be kind of rough there. But what we could do is take some graphics. We could get an artist to paint what looks like the greenery on the side of a mountain, or maybe snow-capped parts, and we can apply those graphics on top of the rocky terrain there, like a decal. You know, you're layering it over. And when you do that, you end up with something like this. From a distance, tell me that you wouldn't think this was an actual real photograph of maybe Yakima if it got a little bit greener in the spring. Okay? But all this is taking that grid, finding the center, raising, lowering, finding the endpoints, raising, lowering, dividing that grid into 4 grids, and successively doing that over and over until you have something like this, and then we just apply the artist's pretty pictures on top of it. And you have created your own fractal landscape. So you can Google that, fractal landscape or fractal terrain, and you can see all sorts of examples. In fact, you can download your own program to build a whole planet. This is a program called FracPlanet, for Fractal Planet. It's open source. You can go download it tonight. And when you do this, you can make your own planets, and you can go zooming around and see the virtual world that you've created, just like Industrial Light and Magic did for Star Trek. Except it's not going to cost you $10 million. It's free, and this will be generated in less than a second. Whereas the Industrial Light and Magic team spent I think it was 1.5 years generating that video for Star Trek II. It's amazing. It's Fractals. All right, now we're getting to the granddaddy of it all. This is my favorite one, because this one shows up everywhere, and I'll show you pictures of this. We are going to talk about the Fibonacci sequence. This one says that the current value of f is equal to the sum of the previous 2 values. This one we're going to start with 0 and 1. 0 and 1 equals 1. I'm glad we all got that. So now what we're going to do is take those last 2 numbers and add those together. So drop the 1 and the 1 down, that equals 2. Drop the 1 and the 2 down, that equals 3. Drop the 2 and the 3 down, that equals 5. 3 and 5, 8. And this keeps going. So it's 0, 1, 1, 2, 3, 5, 8, 13, 24, 31, 21, 34, 21, 34. Mixing my numbers up. It just keeps going. All right, why do we care? This is where you pull out your graph paper, please. What I want you to do, somewhere around, not quite the middle, but just a little bit off to the left of the middle, I want you to draw a square. Just a one grid square. So we'd call that a unit square. Okay? That's the first one. Right next to it, I want you to draw another square of the same size. That's the next one. Okay? Now what I want you to do is draw a square on top that is the same width as those other two squares combined. Hey, wait a minute. That's like the Fibonacci sequence. I have 1 and 1, and I add them together, and I get 2. Okay? So we've got our 3 squares on there. Now I want you to draw another square to the left. This time the size is going to be 3 because 1 plus 2 is 3. Guess what I'm going to ask you to do next? Draw a square below of size 5 because 2 plus 3 is equal to 5. And now one more time to the right. A square of size 8. Okay? So great, we've got a picture of squares. Awesome. It kind of looks like a P.A. Mondrian painting. Doesn't really look like much. Here is the magic. This is why we're drawing squares. If you inscribe quarter circles inside of those squares, you get a spiral. So you see what I did there is draw from one opposite corner of the square to the other an arc that happens to be a quarter circle. If you filled it all out, it'd be all the way around. Then I'm going to keep going with that arc up to the next corner. And now the arc starts getting a little bit wider in radius, and then it gets a little bit wider, and then it starts getting a lot wider. Does this spiral look familiar to anybody? Because you see it everywhere in nature, like in a nautilus shell. The shape of a nautilus shell roughly follows the Fibonacci spiral. Okay? It's not just nautilus shells. We'll get that in a sec. First, I need to introduce you to something called phi, the golden ratio. It turns out when you draw all those squares on the paper like that, the ratio of the width of your rectangle to the height is 1.61803398875. It goes on forever. And if you measured it just 1 against 2, obviously it's not 1.6, it's 1.5. Come on, 3 divided by 2. But as you make the thing bigger and bigger and bigger, it gets closer to this thing we call the golden ratio. We call this phi. It's a lowercase Greek letter phi. There's a couple ways to write it. For whatever reason, the golden ratio is always drawn with more of the handwriting style lowercase phi instead of just a circle with a line through it. Okay? I find that really, really poetic because if anybody saw the flyer for tonight's event, the petals in a rose are arranged such that they create a spiral of petals that approximates the Fibonacci spiral. In fact, just about every flowering plant that has a collection of petals like this has a spiral in it, or leaves in a cactus has a spiral in it that approximates this. And I just thought that was kind of poetic because, this lowercase phi sort of looks like a rose. So I thought that was nice. All right. I told you it's everywhere. And I mean, this is everywhere. The nautilus shell. Got it. This is why I had an egg on the first slide. The curve of an egg follows the Fibonacci spiral here. Here's a cactus. Notice the petals. Oh, I'm giving it away. Oh, crap. Here we go. Wrong button. The petals arranged in the cactus here all follow that Fibonacci spiral. They all roughly have a proportion of the golden ratio. Hurricanes. If you ever look at the spiral of a developing hurricane, it approximates the Fibonacci spiral. Galaxies. If you measure the dimensions of the arms of galaxies, it approximates the Fibonacci spiral. This is everywhere in nature, and it all is modeled on F equals the last F plus 2 F's ago. That's it. How does something so simple give rise to the whole universe? I don't know. I'm not nearly that smart. Yeah, well, I have no answer for you. The human body, and in fact, virtually all mammalian bodies, follow the golden ratio. For most people, darn it, I keep doing that, the height here relative to the fingertip to the opposite shoulder is approximately the golden ratio. Your arm, your forearm to your hand, this would be the 1, this would be the 0.618. Okay, put it together, 1.618. Okay, it follows that ratio. For most people, the bones, if you try to do this with your fingers right now, all the flesh around it kind of screws up the measurements, but the bones inside your fingers follow the golden ratio as well. If this middle joint, middle bone of your finger is the 1.0, here's the 0.618. If this is the 1.0, here's the 0.618. Skull structure, same thing. Look at the ear. The ear follows the spiral. And in fact, inside the ear, there's another line that follows it as well. The ratio of mouth to chin, the ratio of eye to the bottom of the nose, it's all approximating the golden ratio. Even down to your teeth. It turns out the width of your primary incisor here is the 1.0, your lateral incisor is the 0.618. The ratio of the width of your teeth follow the golden ratio. It's incredible. Okay, I'll skip right to this. It's in your DNA. The double helix spiral of DNA. The width of a DNA molecule is about 21 angstroms. The height of one double helix spiral is 34 angstroms. Those are two numbers in the Fibonacci sequence. So the golden ratio is encoded all the way down to the very core of our cells. Why is this? Really couldn't tell you. I just think it's amazing. So let's talk about the amazing. Long time ago, there was a little boy, me. I was 6 years old, and my grandfather did something that has shaped my entire life since then. He bought me a Commodore 64. Actually, it wasn't really for me because, you know, he didn't want to do something nice for me and not the other grandchildren. So actually the Commodore was his, but whatever. He bought it because he thought these computer things were going to be really important. This is about 1982. Using this computer, I discovered whole worlds. I could do the Fibonacci sequence. I could do the Mandelbrot set. I could make my own fractal terrain. I could model anything that I wanted to. I could explore worlds that had never been seen by anyone else. It was just the most amazing play toy for me because it was a play toy that had infinite potential. And yet, can you hear my phone there, darling? This iPhone 6 has 11,000 times the processing power of my Commodore 64. It has 32,000 times the bandwidth capacity. And it has, what was the number? Something like 600,000 times the storage on this phone. I think that's amazing because I have this guy now. This is Finnegan James. He's 2.5 years old. He's my son. And like all good baseball fans, he's a Cardinals fan. Sorry, Gwen. He will see this as a pathetic toy by the time he gets to the age when I was starting to code and explore these virtual worlds. He's got access to whole data centers. He's got access to the internet, cloud services like Amazon.com's AWS service here or Microsoft Azure. By the way, if you didn't know this, Seattle is the capital of the world for cloud computing. There's nowhere else that does it like us. Everybody that wants to play in cloud computing comes to Seattle. This is the environment we're operating in right now. We basically, for all intents and purposes, as far as any of us are concerned, any one of us has access to infinite computing power, infinite disk storage, and infinite bandwidth to explore all the data that the human race has collected on the internet. Finnegan James is not going to build worlds to explore. He is going to invent universes to explore because he can. And it's my job as a parent to give him the tools that my grandfather gave me so that he can achieve this kind of stuff. Science, technology, engineering, art, math. These are all just sides of the same coin. And it's that last word there, math. Everything we do comes down to math because everything we are comes down to the golden ratio. The world around us looks like fractal terrain. The Mandelbrot set, while it exists only in a virtual world, exists as a world to explore just as much as any of the world around us. Science, technology, engineering, and yes, even art are all based in math. So the most important thing you could do for any child growing up today is to teach him or her math and understand basic math and show them that math is not just homework, that math is literally the telescope that Galileo looked through, that math is literally the piece of paper that Einstein, figured out general relativity, and the quantum mechanics guys figured out how the universe fundamentally works. Math is the key to everything that we do. So anybody you know who's got kids, give those kids math. Give them books, give them computers, give them the training that I got, and they can do literally anything in this universe. And that is my talk. Thank you very much. Yes. Let's go do some math. All right. So real quick before we get into the Q&A, some resources. There are two books that I found very fundamental in my self-taught education on this stuff. One is The Fractal Geometry of Nature by Benoit Mandelbrot. That one is pretty deep, pretty techy, but it's got great pictures. The other one, this is a book. I don't know what happened to my copy. This is probably the most important computer book I ever bought in my life. And I haven't told my wife yet, but I actually just bought another copy last night because I wanted to have one for Finn someday. Oh, did you? Okay. Exploring the Geometry of Nature talks about all these things and more and gives you very simple code that I promise you even a high school student could understand and use to explore all this stuff. Google search terms. I didn't have Google back then. I had to get all this knowledge out of books, out of magazines, talking to people. I literally would, whenever we did high school field trips to universities to go to the library, I'd sneak off and go find computer science professors and just grill them on stuff. Now we've got Google. You can just Google any of this stuff and find more information you'd ever want to know about it. I can't wait to see what Finnegan's going to be able to do with this stuff armed with Google. I'm afraid that I'm going to teach him some stuff and he's never going to need my help again. He's just going to come back and say, hey, Dad, look what I did. It's so cool. Some things on here we didn't talk about. I've got some other slides for if we have time to mess around. Cellular automatons, diffusion limited aggregation, Conway's game of life. These are all fractally and iterative kind of things. Julia sets. I don't know what happened to the word set there, but Julia sets is a variation of Mandelbrot sets. Creates more interesting kind of snowflake patterns and spirals than the Mandelbrot set. Frac Planet, if you really like Star Trek at all, you just owe it to yourself as a fan to go download Frac Planet and recreate the Genesis planet. Yeah, so that's what I got. Grill me.
Awesome, thank you very much. We're going to open it up to questions now. I actually do want you to get back to the game of life, because I was always kind of fascinated.
Okay, yeah.
That's how I first learned about this stuff. Also, I'd like to say I wish I had a math teacher half as good as you, because I really got it. All right, questions?
Sure.
This is a little unusual, but if I 2 weeks ago, I was driving to SeaTac to leave on a business trip, and the windshield on my car was struck by a very large rock. So the fracture pattern matches the spiral. It's actually outside if you want to see it, but looking at it from the front, it looks like you're looking at the bulb of a rose. And like individual little petals all forming together, and then one line coming out that's the extension of the spiral.
Mm-hmm. That's cool. I haven't seen an autoglass fracture like that, but what an interesting segue into one of my other slides. Thanks for that. Those kind of patterns, like I said, they just keep showing up everywhere, right? This is something called a diffusion limited aggregation. I don't even know what that term means, honestly. No idea. What I do know is that when you do the math, it's simple iterative math, I'll talk about in a second, you end up with this kind of crystal pattern that looks an awful lot like this crystal pattern. This is silver nitrate. Silver nitrate was a chemical originally used in daguerreotype cameras. It is photoreactive. It turns dark brown when you get a lot of light on it. That's why daguerreotypes are brown, because it was all silver nitrate. But the crystal underneath looks just like this. So how is this generated? And this, I'd say this is a seg from the auto glass, because, I don't know, when my windshield gets cracked up, it kind of does a fracture like that. What you do to do a diffusion limited aggregation is start with a dot right in the middle of the screen, right there. And then draw an imaginary circle around it and pick a point on the circle, any point, doesn't matter. And you put a particle there. And then you start doing what's called a random walk. You say, hey, particle, roll the die. Oh, I want you to go up. It goes up. Roll the die. Oh, I want you to go left. It goes left. And you keep doing that and just let it wander around the screen until either it falls off the screen or it hits your point in the center. And as soon as it either goes off the screen or hits the point in the center, you pick another point on the circle and do another random walk. And you keep doing that. And as your collection of things that have hit each other grows, it just naturally ends up looking like a silver nitrate crystal, like this, like a snowflake, like a fractured piece of glass. Patterns show up everywhere. And we call this a fractal. It's not an organized fractal like the Mandelbrot set or like our dragon or anything, because it's more random. But even though it's random, it still has elements of self-similarity. This whole, oh, I lost it. This whole branch down here off the middle is made up of little branches, and each one of those little branches is made up of a smaller branch. What else is like that in nature? I don't know, trees, leaves, fern leaves. Those are all classic fractals as well. If you Google fractals, you're going to find all sorts of tree generators and fern leaf generators and stuff like that. Stuff just shows up everywhere in nature. It's amazing. Getting all excited again. Next up. That was awesome. I actually would like to see it afterwards. If we can.
Yeah, it's outside.
Yeah, I'd love to see that. That'd be awesome.
I want to throw something else in there too. That's the kind of stuff that if you guys take a photo of it and post it to the Steve Events Facebook page, it would be fantastic. So thank you.
Ma'am.
I'm a huge fan of the golden ratio, but some of the depictions seem really dry, right? So you were showing the picture of the human and going over to this. Now, if you had said in the middle, over to the end, you know, it's like, oh, that's amazing.
That's amazing.
But it's
Yeah.
like, oh, the shoulder, really?
Yeah. Yeah.
So, I mean, are there things that just don't fit?
Absolutely. And I actually meant to talk about this. The reason I titled those slides "Beauty in Fee" is because a lot of what we interpret as traditional beauty when we look at another human being actually comes down to how closely their proportions follow the golden ratio. And if they don't follow the golden ratio, we say, oh, they're different. I'll give you a concrete example. Look at my forearm here. That is way longer than the 1.0 if this is just the 0.618. So we call me gangly, because I don't conform to the golden ratio here, right? I saw an article one time when this research was first done and people said, holy cow, wait a minute, this is all about golden ratio stuff. The picture that they used to depict, we'll just politely say, not beauty, was actually Lyle Lovett's face, the country singer, or Western, whatever he is. He's got a very tall face and narrow. His forehead is too big because it doesn't conform to the golden ratio. There's another thing, the symmetry of eyes and stuff. That's another contributor to our estimation of beauty. But yeah, nature does not adhere to the golden ratio. It approximates the golden ratio. It's kind of like a variation on the nature versus nurture thing in psychology. In this case, though, we're talking about genetics versus real-world growth. The golden ratio is encoded genetically somehow, who knows, but it's encoded genetically such that the body will approximate that in the ideal. But different things happen. Different molecular reactions cause your bone growth areas, growth plates, whatever they're called in bones, to maybe grow a little bit faster than they should. And so you end up with someone with, very long femur, and the muscles don't actually grow as fast because the bone was a little bit different. And then you end up with a poor guy who did karate for years and was always having pulled hamstrings because it didn't conform to the golden ratio. It just kind of approximated it. So we start out being perfect, and as we grow, we get a little less perfect. But yeah, it's an approximation. It's not a strict rule. If we measured all of us today, we'd probably find that none of our faces completely complied to the golden ratio. Actually, just looking around, I would say Nicodemus here has the best chance of his face conforming to golden ratios. That's okay. My wife's face doesn't quite conform to it. Still love her dearly. So.
If you averaged us, do you think it would?
Yes. Yes. With a large enough body of faces, the strict average would end up conforming pretty closely to the golden ratio in the appropriate places. Yeah. Yeah. Yep. What else? So I still got more slides. If nobody asks questions, then I'm just going to keep talking.
What's the most...
Oh, yeah, sir, please.
I'm a contrarian. I actually
sure.
think that computers have diminished our ability to comprehend math. I think it's too easy to just code something into a computer. And I see this, I'm an engineer, and I see young people come to work for me, and they do not have what I would call numerical intuition.
Yes.
They
Yes.
cannot look at a set of numbers and estimate what's going on without going to their phone.
Yes.
I actually think the computer revolution we've gone backwards.
Yeah.
Those
So,
equations that you put up there, a 6-year-old will those into their computer. And
Yep.
have absolutely no concept of what's really behind it.
yeah, and that's exactly, that's a great point. That's exactly what happened with me. I didn't even know what the little 2 up in the corner, when I first looked at the Mandelbrot equation, I had no idea what that squared notation was. Because I think I was 8 or 9 when it happened. Had no idea. I had to find out a book. Actually, the way I learned it was when I looked at the source code in the article, it said z squared, and I looked at the corresponding code and it said z times z. It's like, oh, that must mean multiply it twice. Okay. I didn't know. All I knew is it made pretty pictures. But it got me really interested in this stuff. And that drove me to become good at numerical methods, good at arithmetic, good at solving equations. Though I got to Calc 3 and gave up on the integral calculus, and I was like, what do you mean I can't do an integral of this equation? Math is stupid. I'm going back to my computer. So let me, I will say I totally agree with that. Yeah, kids these days, they don't know how to do math. It's true. It is honestly true. When I took the AP calculus exam in my senior year of high school, I was absolutely not allowed to smuggle a calculator in. And kids who did smuggle calculators in were kicked out, and bad things happened. Now, you get to actually take a graphing calculator into the AP calculus exam. Oh, it's crazy. Here's where I'll be contrarian, though, to your contrarianness. What computers have enabled us to do is go farther into theoretical mathematics, farther into physics, farther into engineering. Yeah, we pay the price by people at the low end, at the beginning end, not having the skills that we all had to have to get there. But what we're doing is enabling the more theoretical of our next generation to stand on our shoulders and get even farther than we could get before. Like basically all particle physics now, to do particle physics, you have to be a good software engineer. It's just what has to happen anymore.
Well, I think what's happened, what I read was that there used to be 2 branches of science, either a theoretician or you were an experimental. But now there's a 3rd branch, which is simulation.
Computation simulation, yep.
Basically, you can simulate a universe that's good enough to act as the real thing.
Yep. Yeah, it's a tough one. In all the fields, maybe art doesn't struggle with this one so much as science, technology, engineering, and mathematics, which also is very dependent on software these days. We have to figure out the new balance. You know, we knew the old balances. I think when I was in engineering school, it was the same kind of way. You had to be good at arithmetic. You had to be good at math. You had to be good at calculus on paper to even get to the point where you could use the calculators and the computers. But that inherently limited what I could do, what I could imagine. I couldn't really design a microprocessor in college until I had computers that could simulate the microprocessor. I'm not nearly as talented at that stuff as the people who built the microprocessors originally by literally drawing on pen and paper. You know, it's amazing. But because we have those computers today, we've been able to build things like the, you know, Intel Core i7 processor, which is just god-awful powerful compared to my crappy little Commodore 64 running an 8-bit 1 megahertz 6502. Yeah, I mean, these days, we don't even use 6502s as subcomponents in computers. We use bigger chips just to handle things like talking on the internet. Like 6502 doesn't even power pocket calculators anymore. So that's kind of awesome. I don't know, we'll find a new balance, or we'll find one. I don't think that civilization is going to implode because we can't do math. However, we are at risk of getting to a point where we can't keep going because there's a chasm between knowing nothing and being able to use all the tools we're inventing today. And we have to make sure that we've got people in that chasm that have the skills that you and I, you know, came up with in engineering to be able to keep going. So it's going to be tough. We're going to have to figure this one out. What's up? Okay, who's next? I think Michael had a question.
So one of the things that we look at CVent is looking at the future, whatever that means to you. Pick a time scale: 5 years, 10 years, 25 years. When your kid grows up, what does the future look like when you're considering this kind of technology? Where is this? We're seeing it in nature, but where is it also going to show up in the world that we live in?
Okay. Good question. I'm going to answer in an optimistic way and a pessimistic way. We'll start with the pessimistic so we can end on a good note. The pessimistic way, and this relates, I'm sorry, sir, I don't know your name.
Peter.
Peter. This relates to what Peter was talking about. Advancing technology does not mean that kids are born fresh from the womb smarter. We all still start at the same place. You know, insert caveat here for evolution, which moves much more slowly than Moore's law. We all start at zero. And yet the endpoint for knowledge and ability keeps extending out. We are rapidly creating a society where the gap between knows and knows not is manifesting as haves and have-nots. Okay? Education is so ridiculously critically important because we're getting to the point where, hey, technology is making jobs go away. There's a bunch of economists that say, oh no, as technology increases, jobs will keep increasing. That may be true, but the kinds of jobs get smarter and smarter and smarter. Okay? There's only so many garbage, you know, truck operators that can exist in the world. We have to make sure that we are educating people so we can cross that chasm and we can keep having as many haves. You know, actually we should have more haves than we have today than have-nots. And that starts with knowledge. That starts with education. And as I made the point earlier, that starts with math. That's the basis of all of it. So that's the pessimistic side. We really have to watch that so that we don't create a more unequal society based on the advancement of technology. That's a risk. Here's the optimistic side. Technology can be, if applied correctly, the ultimate democratizer. We've seen this in the internet. I knew when I was a freshman in college, 1990, this was spring of 93. I was on a chat room and I was talking to 2 Israelis, a German, a Frenchman, an Englishman, somebody in Scandinavia, can't remember where, somebody in Japan, and then several people from the United States. And we were having a discussion about nationalism. Think about that audience, talking about nationalism. That was an interesting discussion. And yet, we were talking constructively about it. We were talking peacefully about it. We were having a meeting of minds, not a meeting of guns and tanks. That to me was amazing, and that's when I knew this internet thing was going to be a great thing for the world if used properly. Revolutionaries, when the Soviet Union was falling, were using the internet to communicate with each other. We've seen really neat ad hoc networks out of mobile phones being created in Hong Kong. Even though the authorities shut down all the cell towers, people were creating a local internet through each other's phones, something called an ad hoc network. And they were still able to coordinate and fight the oppressive authorities. That's amazing. What you're seeing is technology being, amazing technology being able to be used and applied by individuals, okay? So I don't know, I didn't know what the z squared plus c thing meant when I was first coding. I bet there isn't a single person sitting in the protests in Hong Kong that can actually explain to me the Bluetooth protocol at the bit level that they're using to construct an ad hoc network. So what? They're still using it. They're still able to make use of the thing and do, you know, positive things for society. Hopefully it's positive things for society, using that technology. Being able to move things down to the individual level so that anybody has access to incredible computing resources if they want them, like with Amazon's cloud. I'm pointing at Nicodemus because he used to work at Amazon. For literally fractions of pennies an hour, you can rent powerful machines and host things on the internet. You don't need to have big data centers or buy expensive computers yourself. If you can spare $9.76 a month, you can have a server on the internet doing whatever you want to do, sharing information, running calculations, building Mandelbrot sets, whatever. It's incredibly democratizing. I can't wait to see what this next generation and generations do with all of this awesome power. It's all informatics power. And what they come up with. I literally cannot imagine what Finn is going to do with all this horsepower if he decides to get into computers, like Papa. I sure hope he does, but if he does, I can't imagine it. I just know it's going to be incredible because our several generations represented in this room landed somebody on the moon with what amounts to a pocket calculator by today's standards. We did that. We've built nuclear power plants. We've put satellites. Let's see, Voyager is now 18 light hours away from our planet. Doesn't sound like much, but when you actually do the math, it turns out to be an incredible distance. It's amazing what we've done. And we're talking about all the things that I've talked about right now. We're done with mid-1960s computing technology. That technology made my Commodore 64 look like today's cloud, okay? I can't even imagine what we're going to do. We've found the Higgs boson. Holy cow. That's amazing for particle physics. You know, so Ray Kurzweil. Anybody heard of Ray Kurzweil? Futurist? Yeah. He says that if you follow Moore's law, which says that the amount of computing power for the same cost roughly doubles every 18 months, if you follow that, by 2025, your average desktop will have enough horsepower to simulate a human brain at the molecular level, okay? That's just simple math. How you get a human brain into a computer, how you digitize it, we haven't solved that problem yet. People are working on it, but it's tough. But we'll have the horsepower to do it. By 2045, your average desktop, again, that will cost as much as it does today, so figure $1,000. Your average desktop will have enough computing horsepower to simulate the brains of every person on Earth. And every one of us could have that kind of computing power.
Is that a good thing?
I have no idea, but I sure can't wait to find out. I subscribe to the Star Trek theory of the universe of the future, which says that, yeah, there are going to be some bad spots, but overall it's going to be pretty awesome. Call that my religious faith. I have to believe that it's going to get better, not worse. Otherwise, I'm going to get real sad. So we'll see. We'll see. Sir Adam had his hand up first, and then we'll get to you. Yeah.
I was going to ask you to speculate wildly on whether or not reality is fractal.
Oh, great question. Are we living in the Matrix? Do you remember, they just did a research project on this. Somebody came up with a way to try to measure whether we were living in a computer simulation, and I can't remember the answer. But here's some fundamental facts. You judge. There is a smallest distance in the universe that you can measure. What this means is the entire fabric of the universe ultimately is a piece of grid paper. That distance is called a Planck distance, named for Professor Planck, physicist, Max Planck, thank you, P-L-A-N-C-K. As well, there's a fundamental smallest amount of energy that's called a quantum. That's where quantum mechanics comes from. So if you have a smallest amount of energy and a smallest amount of distance, and there's been some speculation, I've seen this pendulum go back and forth a couple times, whether there's a smallest amount of time, often called a jiffy. That sounds like you're living on a piece of graph paper to me. Right? Yeah, be there in a jiffy, right? Well, Einstein said that time and space are equivalent. Remember, that's part of relativity. So what that means is if there's a minimum distance, a Planck distance, then according to Einstein, you should be able to translate that to time as well, since time and space are equivalent dimensions. So yeah, it starts getting really fun when you start thinking about that. Are we living in a matrix? I don't know, but we're certainly living on a piece of graph paper. Whether God created that or it naturally occurred, or we are some 6-year-old kid's computer experiment who doesn't understand what the squared notation means, but oh my God, he accidentally created a universe. Who knows? It's fun to speculate. Yeah, sir.
Do you personally believe that at some point in the future time travel becomes possible?
Oh boy. Okay. We are totally speculating by someone who doesn't have nearly enough physics to answer that question properly. But from my casual readings of quantum mechanics and all the eigenstate math and all that crazy stuff, I know Chris is over here laughing. He's like, you casually read quantum mechanics stuff? Yeah, actually I do. It sure seems like the multiverse scenario is possible, where there's an infinite number of universes that are constantly splitting off from each other, where in quantum mechanics, quantum mechanics is fundamentally random. You throw a die, at least our understanding of it now. Different things could happen based on probabilities. What if all probabilities happened simultaneously in a, n to the nth set of multiple universes? If that's the case, I don't see why we couldn't do time travel in the physics sense. Whether something as complex as a human body could do time travel, I highly doubt it, because the bigger an object you have, the more the quantum probabilities coalesce towards a certainty. So I don't see it happening. It could probably happen at the particle level. In fact, it may be happening at the particle level. That's one of the interpretations of zero-point energy that says that particles and energy just spontaneously erupt in the universe and then annihilate each other and disappear constantly. So maybe it is time travel that's making that happen. Don't know. But I don't think human beings are ever going to be able to do it. Which sucks, because I really want to go back and meet, like Einstein and stuff.
Well, if your opinion were in the other direction, then it would, the arguable case would be that we have people from the future that pass amongst us.
True story. As totally screwed up as our Congress is right now, I just don't see how that's possible, unless they're actively sabotaging us. Ma'am, yeah, there we go.
So I heard that your company works with artificial intelligence.
That was my interpretation.
It's, so yeah, from
well,
the, yeah, go ahead.
Maybe you can answer this question anyway.
Yeah.
So I took a few courses in artificial intelligence in the late 70s.
Mm-hmm.
And it was going to be in 10 years.
Yep.
We're going to have this breakthrough, right?
Yep.
And Hal from 2001 was born in 1997.
Yep.
This has not happened. This is
Nope.
one thing that we have not done. But we do seem to be on some sort of precedence for this. What do you think?
I think we've been on that precipice for a really long time. And so I've given up, because when I first read about this stuff when I was younger, I thought it was 10 years away as well. It's just like fusion power. Fusion power is always 10 years away and has been for the last 50 years. Artificial intelligence is 10 years away and has been for the last like 60, close to 70 years since people started thinking about it. It appears that intelligence is an emergent property. Remember I said earlier when we were talking about the dragon curve, how its simple lines generate emergent complexity. So starting with simple rules, you can create something that looks terribly complex. But if you know the secret, you know how to take it apart down to its root level. Okay, intelligence. is clearly something that's very complex. The number of potential interconnections in the neurons of your brain exceed the number of atoms in the universe. Figure that puzzle out. That paradox takes a little while to cook through, but it's amazingly complex up here in the gray matter. How simple things like nerve cells, neurons, somehow getting put together create intelligence? I don't know. But I also can't answer the question of why taking a V and then replacing each leg of the V with another V turns into the dragon sweep, dragon curve. I don't know. But we know, this is, by the way, chaos theory and systems theory deal a lot with these things. Systems theory is a lot of fun. It talks about how emergent systems behave. Let's go to, okay, Conway's Game of Life. This is something called a cellular automaton. It has very simple rules. The rules are, for every square in the grid here, if the square has, let's see, if the square has 2 or 3 neighbors, then the square gets turned on. If the square has more than 3 neighbors, it's overcrowded and the square gets turned off. If an empty square has exactly 3 neighbors, then it will turn on. Okay? That's the rules.
Turning on means you become
become black, like fill in the square. Okay, so we call that we call it being filled with a dot. We call that being alive in the game of life.
So having an alien black dot.
Yeah. If you have 2 or 3 neighbors and you're black, you stay black. If you have more than 3 neighbors and you're black, you go empty. You die. And if you have exactly 3 neighbors and you're dead, then you become alive. It's reproduction. Being alive means you get a dot in there. You get a black cell in there.
Relative to the other guys, you are...
Yeah, you now become a neighbor. That's right. And so you calculate each successive generation. Hey, there's that iteration thing again. You calculate each successive graph using the existing graph, and then you replace the existing graph with your new one, and you keep doing that. Over on the left here, we see something that just kind of started out with a random collection of dots. And you know, all sorts of stuff's going. It's kind of chaotic, doesn't really do much. It's kind of like molecules in you know, a primordial soup. Most of the time they're going to bump into each other and absolutely nothing interesting happens. However, there are certain patterns in Conway's Game of Life that show organization. Okay, see these little guys over here? You'll see one here, here. Those are called gliders in the Game of Life. All they do is go in a diagonal direction, either up or down. That's what they do. This messy group of dots up here is what's called a glider gun. Just by being there and following those ridiculously simple rules, the 2 or 3 or 4 or whatever, this glider gun produces gliders that get shot off. Okay? Obviously, it's not artificial intelligence, but what it is showing is that very simple rules can give rise to very complex things. In the real world, this is like the very simple rules of a hydrogen atom, a helium atom, an oxygen, or let's get specific, a carbon, a hydrogen, and oxygen bump into each other and create a complex hydrocarbon molecule.
Well, I have a question.
Yeah.
Said you've got to have a certain number of neighbors.
Yeah.
If you change that by 1, does it always fall apart and doesn't work?
Yeah, so a guy named Stephen Wolfram, who's, yeah, you know Wolfram, yeah. Yeah, exactly. He created Mathematica. He wrote a book, what's it called, Nicodemus? His big tome on cellular automatons. I can't remember. He wrote a big book. It's all about this, except in his book, he said, what if we change the rules? What if we change it to 3 neighbors or 4 neighbors, you stay alive instead of 2 or 3? And he ran through a whole bunch of combinations and created a general mathematical framework for talking about these kind of things, and found all sorts of interesting patterns in there. Other, you know, self-recursive things, other organization. The book is like seriously 3 inches thick. It's a great read if you have a year. But this kind of organization is not very interesting in a small scale. I'm going to show you a slightly bigger one now. This thing is called a breeder. This breeder creates glider guns as it travels across the screen. Those glider guns create gliders shooting off the side. Let's watch it go in motion here. So there's a glider gun. We saw it side to side before, but now it's up and down, and here's its gliders that it's shooting off. Oh, here's another glider gun shooting stuff off. Here's another glider gun shooting stuff off. And some gliders here collide with the detritus that it leaves behind to create more glider guns. This pattern took decades for people to discover. In mathematically speaking, it's kind of like evolution. We're the energy. Human minds and computers are the energy being pumped into the system. And it just took time for these things to arise, for random combinations that human beings tried out to generate this kind of complexity. Using this pattern, people have actually built games of life that are fully functional microprocessors, where the gliders, oh, damn it, I did it again. The gliders here are the bits, are the ones and zeros, the electrons moving through the system, and they've created gates for logic, and they can actually construct a whole processor out of the thing that takes a monumental amount of computation time to run, but it can be done. So looping all the way back around to artificial intelligence. I have no idea when we're going to do it, but I have a strong suspicion that it's just going to be a whole lot of people trying out a whole bunch of different combinations of things, and one day we're going to trip over the combination that actually works. And we're not going to have any idea that we've succeeded, because it probably won't be a human intelligence that we're dealing with. It'll be so alien, we probably won't even recognize that it's intelligent, because it doesn't have the same experiences that we have. When we talk about intelligence, most of what we talk about intelligence is actually social habit, with a little bit of extra thinking on top. The part of the brain that is differentiated from other apes is the neocortex. That's a 1 to 2 millimeter thick sheet of neurons on the outside of an ape brain. Okay, volumetrically it's something like 1%, not even 1%, and that's what gives us thought. We're really just social apes that happen to have a little bit of extra something on top that allows us to think about shit like this. Sorry, stuff like this. Okay, that's it. That's it. So what if a different kind of combination sheet arose? What if we were lobsters instead? Would we recognize it if lobsters became intelligent? Think about lobster cavemen. What did cavemen do? They just hunted and, invented fire. Well, lobsters being at the bottom of the ocean probably aren't going to invent fire, but they're going to spend most of their time hunting. They're going to develop social patterns that allow them to cooperate to build, to hunt their prey, whatever lobsters eat. I don't know. But would we recognize that?
They created art.
Yeah, isn't that cool? Yeah, the little patterns in the sand, yeah. Is that intelligence? I don't know. Would we recognize it? I don't know. Yeah. So it's fascinating. There's so much interesting stuff in there. What most people think of as AI is really just being able to solve human problems faster and more effectively. So we're not building artificial intelligence. We're building things that are good at solving a problem. Yeah. So, I don't know. I'm excited about it. I, for one, welcome our robotic overlords. You might remember that Ken Jennings said that in Jeopardy when he got his butt kicked by an IBM computer. Yeah. Michael.
Okay. Does anybody have any other questions? Because we're running up on 9:15 and almost 9:30. So I want to be respectful for everybody's time. Does anybody have any last questions? Okay. Well, thank you very much.
Yes. Thank you. Thank you.